So, hello everybody. Yeah, I'm Dario. So I'm a joint research fellow in the Branco lab and also in Magic Sahani lab in Gatsby. Thank you very much to Matteo and Nick for inviting me this year to give this talk. So yeah, so mainly the talk.
Dario, try to let go of the microphone. Just let go of it. Just don't touch it. No.
Don't touch it. Okay.
Yeah. Talk because it's quite loud otherwise.
Okay, can you hear it well? Because usually it's very bad.
No,
okay.
it's perfect.
It's perfect. Okay, awesome. Yeah, so as Matteo was saying, the talk will be mainly about on the technical aspect on implanting a NeuroPixel probe for chronic recording in free moving mice. And yeah, I'm gonna go through all the steps on how to prepare a probe and then implanting it and then doing a recording. And then I'm gonna talk a little bit about also how you can recover the probe after you have implanting it. So yeah, so before I go forward, just a couple of acknowledgements. So I want to thank, so you will see a lot of pictures about the surgery and the preparation of the probe, which has been taken by Seppi, which is a postdoc in Troy Margaret Lab. And also want to thank Diego Gutniewski, that was the postdoc who basically teach me how to chronically implant silicone probe in mice while I was doing my PhD in Svoboda Lab. So as I say, I'm going to focus mainly on the technical aspect of the implantation. So if you're curious of how we use the data that we recorded from these mice, you can just have a quick look to our preprint that recently came out in bioRxiv. So let's start from the end. So this is a mouse that was chronically implanted with the NeuroPixel probe. So you will see this here just to show you, just after 2 hours from the surgery, the mouse can walk around very happily and move his head very, very smoothly around this cage. Oh yes, so before I go more, give you a more detailed description on the surgery, so I want to just point a couple of things. So first of all, the probe I'm going to show you are an older version of the probe, this phase 3A, and I guess what you guys are more familiar with are these NeuroPixel 1.0, which are the one which are commercially available. So I just put here a schematics if you want them to go back to this slide, just to compare the two, but they are very, very similar. So whatever I'm going to show you, it also basically apply to the NeuroPixel 1.0. And also another thing, you may have noticed that there is an head plate on the mouse that I will show you. This is not necessary, so you can do the same type of implantation without an head plate, cementing the probe directly to the skull. Okay, so the very first thing you want to do before implanting the probe is to do some preparation. So the first thing is to connect a ground wire to the probe. And yeah, in order to do that, you need just to solder this cable that I put here, the specs. This is a very nice one that I found, which is very small, the diameter is very small, it's very flexible, very soft, so you can handle it very easily during the surgery. And at the end of this cable, I connect this ground pin, which is the female ground pin that will be connected on the male ground pin that will be on the mouse skull. So after that, the next step is to cover the probe with this epoxy resin, because you can see that there are many exposed electronic components that you want to protect, because you don't want saline to go there during the surgery, or maybe after the probe is implanted, the mouse to put some dirt on that part, so you may have a short circuit. And yeah, so what we do is to cover with this epoxy resin this part of the PCB. And yeah, so I usually wait 24 hours after I've applied epoxy, because it can be quite sticky, and even if they say it sets in 5 minutes, it's better not to risk it. So all of this usually do the day before the surgery. So of course, when you want to implant a probe, you want to have it mounted on a stereotaxic frame. So what I use is this holder that you can buy. I put the detail here. You can get it from NeuroNexus. I guess now you can also use the dovetailed holder for the new generation of probes. And basically what you do, you can see you basically have this clamp here with two screws, and you just put a little bit of double-sided tape here that will help holding the flex cable. And this is how it looks. So you just sit the probe inside the clamp, and then you have these two screws, and you just have to basically tighten them until the PCB of the probe stop moving. Then this holder is nice because you also have this other screw that you can play with to get the shank parallel to the post. So then when you're gonna put, when you're gonna penetrate the brain, the penetration will, the shank will be basically parallel to the direction in which you are moving it. Okay, then of course, whenever you do a chronic implant, you want to be able afterward to reconstruct the track of the probe in the brain. So we use either dye or Dario, so basically orange or green color. And this is just an example with the Dario, and you can see here the probe insertion site, and here was the probe tip. So there are two different slices because the probe was going inside with an angle. More recently, we also tried to use a different type of color, which is this cell bright blue, which is blue shifted, and this is put here an example of the probe track. So this is another option, for example, if you want to implant more than one probe, or for example in acute, if you want to do multiple penetration, you can have an additional color to play with. Okay, so after you have prepared your probe, then you go to the surgery. So the way to go is, first of all, we want to remove a large patch of skin from the mouse skull. So in this case, we were targeting retrospinal cortex, which is about here. So the probe will be here. And usually, I try to put the ground pin basically as far as possible from where the craniotomy would be. So in this case, the opposite hemisphere, and since the craniotomy was posterior, the ground pin would have been very, very anterior on the opposite side. For the ground pin, so I show you at the beginning the FINO, the ground pin that was on the electrode, so on the probe. So on the skull, you just buy the same model, but the male one. So the ground pin also requires a little bit of preparation. So you basically have two options. So what you want, of course, is that the pin itself needs to be in contact with the brain in order to provide a good grounding. And so what you can do is to either just drill a craniotomy, and after you have cut the pin, because the full one is quite big, you can just sit inside this small craniotomy you have done the pin, so that the bottom part of the pin is actually in contact with the dura. Or if you want even a better grounding, you can solder a silver wire to the bottom part of the pin, and then you just gently stab the brain with this silver wire, and then sit the pin there. And then
sorry, can I ask a quick question?
Sure.
All of these recordings were done with the 3A probes, which were these early prototypes.
Yeah, that's correct. Yes, that's correct.
So you didn't have the opportunity to try internal referencing, internal grounding, which also...
No, I never tried. Well, okay, I mean, we tried that, whether in cases in which the grounding was totally horrific because of something. Yeah,
so
but yeah.
It is conceivable that somebody who buys probes now, they might be able to use the bottom of the probe as the ground. Yes. Nick, correct me if I'm saying something silly, but I think this is something conceivable.
As the reference. And so to be clear, Dario, you've connected both the ground and the reference to...
Yeah, that's correct. So this is short circuit grounded referencing, yeah.
Okay.
Okay. Yeah, so I say grounding just because this is the way in which usually we talk about it. So in the old probes, we have two pins on the probe, and you can short circuit them, and one was ground and one was reference, and then you have a single wire that you can use for both grounding and referencing. I don't know if now it's different with the new generation. Yeah, so for the pin, in order to secure the pin, what I use is this glue, so this backbone glue, to first fix the pin to the skull, and then you can put additional strength by adding this dental cement that we use routinely in the lab. So this is very nice because it's curated by blue light. So you first apply it and it's still runny. And then after you build it in the shape you want, you can use blue light to make it hard. Yeah, so at this point, after you've put the ground pin, you can kind of see it here. I don't know if you can see my mouse pointer, but you can see this golden part at the very front of the mouse, in front of the head plate. So now it's time to put the probe. So you will. So what we do? So you first drill the craniotomy on your favorite part of the brain, and then you can just go there and penetrate. I usually try to penetrate very, very slowly, meaning that you know, to cover the 3.84 millimeter where you have the active recording site of the probe, I try to take more or less half an hour. So you go in very, very slow step, just, you know, to minimize the damaging you may do to the brain while you are penetrating. And after you get in position, I cover the craniotomy with the silicone elastoma with quick cast, just to protect it. Okay, so at this point, the probe is in the brain. So the point is now you want to fix it to the skull. So in order to do, but there is a problem here, which is that you don't want that the dental cement that you're going to use fall on the shank and damage it. So what we do, we put a very tiny layer of Vaseline between the PCB and the skull. And then on top of this layer, we put the dental cement. This is actually a bit a tricky step of the surgery, but with a bit of practice, it's actually doable. And so after we have protected the shank with the Vaseline, we just built this sort of layer of dental cement. And you try to put as much as you can without, of course, cementing also the probe holder. At this point, you can go there with a screwdriver and release the probe holder. So at this stage you need to learn a bit of a balance between putting, you know, enough cement for the probe not to move while you do this step, but not too much to, you know, cement also the holder, and that would be very, very hard to remove it. So after you have removed the holder, you can just add as much of dental cement as you want to get the probe very, very stable. At this point, you can connect the ground pin. So this is the ground wire that we have previously installed. So since it's very, very soft, you can just bend it and go on the ground pin and connect it. And at this point, I think it's quite important to put additional cement, both to keep the ground pin in place and also to secure better the ground wire to the pin itself. So after this, there is an extra stage, which is to protect actually the probe. So we use this 3D printed box. And the idea is that you will use this box to both protect the PCB and to also have a place where you can put the flex cable, because you see the probe is just this part, the PCB, but then you have all this flex cable, which is very long, and this can be a problem if when the mouse will be awake, walking around during your experiment. So this is the 3D printed enclosure we use. You can download it from this link. And it just requires, after you have 3D printed it, a little bit of preparation, because what I do is to cut this wall of the box, so then it's much easier to insert the PCB inside, and then you can put the wall back and cement it. So just, it's not, I don't know if it's very clear from this picture, that you can see that basically the PCB will be inside this part, and then you will fold the flex cable inside here, and then you will have the connector sticking out here, and you will cement it to this part of the box. And you can see this part of the, in this part here, the connector sticking out from the box. Yeah, so it's very easy. So after you have cut the posterior wall of the protection box, you just put it there, so you can see the PCB in the posterior part, and then you will just cement it to the cement that you have already applied to support the probe. And then you can see here, you fold the flex cable inside the anterior part, and then you will cement the connector there. At this point, you can put back the posterior wall and cement it back. So then the PCB will be fully surrounded by this 3D printed plastic protection. So we are almost there. There is an additional step that I do, which is to add this plastic part to provide additional support to the head stage, because so at the end of the implant of the experiment, the head stage will be sticking out like that. But as you have probably realized, the connection between the probe connector and the head stage is quite flexible. And what happens sometimes is that if you don't do anything about it, when the mouse walks around, this will generate a lot of flexion and can cause disconnections during the experiment, which are quite annoying, because you will either have gap in your recording, or sometimes this causes saturation of the signal, or just if you're using SpecGLX, you will just stop the recording itself. So in order to avoid it, what I do is just to add this plastic part in the front part of the implant. So then you can imagine that when you put the head stage, you can just put a little bit of quick cast between this plastic part and the head stage itself, and this will stop the head stage from flexing back and forth when the animal moves around. Okay, so recording. So here is just an example of a mouse walking around, and will be then loomed and escape back to the shelter. And yeah, just to make a point that even if the mouse has this big implant on his head, you can still use tools like DeepLab Cut to trace, for example, the head direction of the animal while is freely moving in its arena. So for this type of probe, we also adapted a rotary joint, which is commercially available, which I'm not 100% sure it also works for the NeuroPixel 1.0, but if you want to try it, feel free. It's just this model here, and all you have to do is basically to cut the NeuroPixel cable and to solder it to the right pins of a HDMI connector. I know that OpenEFIS is also working on a rotary joint for the commercially available NeuroPixel probe, but I don't know if that's actually ready yet or not. Another thing which at least for the phase 3A probe, I notice is very important, is also to put an additional protection on the head stage, so to epoxylate it. And because what I noticed is sometimes during the experiment, when the animal walk around, you may touch some of this electronic component, and this can cause, again, saturation of your signal or short circuit, which can actually ruin the quality or cause disconnection or spectral X to stop. But if you have a very nice epoxy, if you have a very nice coating of epoxy resin around your head stage on both sides, this fixes most of the problem. Okay, so we're almost done. I went a bit quickly because there were many questions, so I think it's better if you guys ask questions rather than me explain in detail.
Q&A.
Yeah, so just this last thing, maybe. This is the last slide. Yeah,
fine. You're fine with time.
Okay. Yeah. So can we reuse the probe? So because of course the probe are expensive, are very valuable. So maybe you want to reuse them after you have implanted it. And the answer is actually yes. So something we realized, and we're quite surprised, that 90% of the time, after you have cemented the probe to the skull, if you go there and you cut the skull to remove the brain, the whole implant will kind of pop out from the skull with the shank still intact. And so at that point, it's just a matter of removing the cement and the plastic part. So basically so the plastic part is just 3D printed, very thin 3D printed plastic. So it's actually very easy to break it. And then the tricky part, as you can imagine, is to remove the cement from the base of the probe. But this you can just do with a pair of forceps, a pair of tweezers. And it's quite nice because this cement breaks quite easily, and we actually have recovered quite a few of probes by now, and we never broke it in this stage. It can be that sometimes it come out without a shank, but this part is just a matter of being patient, and you can do it. And then you can just mount it again, as I've shown you at the beginning of the presentation. And so this is just an example of a new recording done with the previous probe. I guess it's quite important to wash the probe well, especially. So what we do is to remove the probe after we have perfused the mouse with PFA. So you want to be sure that you really wash it well in order to avoid them, implanting a shank in a brain with PFA on it. So we do this cycle 3 times with tergazine first, then we use isopropanol, and then distilled water, and we remove this. We repeat this 3 times. And you leave half an hour more or less for each of these steps in the solution. Okay, yeah, so that was pretty much it. So I guess I can look at the question and answer.
We have some time, and maybe we can summarize some of the questions. I don't know if Nick has a way to summarize some.
Yeah, sure. So a couple of people wanted to know how much the whole implant weighs.
It's fairly light. I think it's something about 1.5 to 2 grams maximum. So the heavy part is actually the amount of cement you put actually make a big difference. So if you put a bit less cement, it will be much lighter.
And then I guess the head stage too, which is only present during the recording, but
that's correct.
An additional weight as well.
Yeah. So for the head stage, actually, now that you mention it, so what I've learned what I've seen is that usually after the surgery, I don't put the head stage because of course it's heavy and the animal has to recover. But after the first recording, you can even leave the head stage on, and the animals can cope quite well with it. And this would be actually, I think, it makes your experiment much easier because connecting the head stage to the connector is not easy, and you should maybe anesthetize the animal to do that. But connecting the cable to the stage itself is very easy, so you can easily do that without anesthetizing the animal. So what I do actually after the first experiment, I tend to leave the head stage on.
And maybe I'll point out to everybody that there is a paper from Anne Churchland's lab, Juavanet is the first author, that describes a similar implant and quantifies both the weight of the implant and the amount of running that the mouse is able to do with it. I think it would be very similar for what Dario showed you here. So next question is about screws. Do you use any anchoring screws, or do you, or can you use a screw for the ground, or do you need to use the special pin that you described?
No, I guess you can use a screw for the ground. It's not needed to. So I never. So with other type of dental cement, I've used screws to increase the support of the implant because I had some explanting, a mouse that got explanted. But with this type of cement, I don't think you need screws for additional support. I mean, I've never had a mouse explanted in the last 3 years, and yeah, I've never used a screw.
Yeah, so one person asked which dental cement is it, but maybe I think the part number was on the slide, so we'll
yeah, so yeah, everything is on the slide.
We'll leave that. A couple of people ask about cleaning the probe. Do you ever use solvents like acetone or other solvents to try to remove the cement from the probe? Do you just soak the probe, or would sonication also help, or is that a good idea?
No, so actually we try to use acetone not for the probe but for remove this type of cement from head plates, and it doesn't work very well. So yeah, we just use the thing. Also, I mean, I don't know how good it is to put a solvent on the shank. I mean, I never tried myself, but I don't know if it is advised or not. I would be a bit worried. So no, we just use tweezers to break the cement. That's the only thing I've tried. And yeah, to wash the probe, we just use this tergazine, isopropyl, and distilled water, which I think it is also advised in your Neuropixel manual to use this product. But this is just to clean the shank, not to remove the cement.
Next question is, when you insert the probe during the surgery, are you recording at the same time to guide the implant?
Yeah, so sometimes we do that. It is a bit tricky because you have not connected the ground pin yet. So the signal, I mean, you can do that by doing averaging across multiple channels to remove the noise. Or you may want to, or you can try to connect the ground pin first and then do the penetration. I was doing that at the beginning just to be sure that it was in the right place. Then I guess when you get more experience in the surgery, you don't really need to do that. But yeah, that can be a good idea. Then also, I guess it depends what is your experiment. If you're targeting a very small area which has a very clear signature, then maybe you want to do that.
I would probably also recommend it for people who are just starting out as a way to, so that you can realize at what stage the probe breaks, if it breaks. Like if you know that the recording was working while you were inserting it, and then the next day it was broken, then you know that it broke it sometime then. Okay. One question is the rotary joint necessary given that the cable is so long, with a 5 meter long cable?
Well,
why did you decide that was necessary?
Yeah, so for our experiment, so the cable we have with the Phase 3A is a bit different from the cable you guys have, in the sense that it's a bit stiffer, and it was very important. I think, so for our type of behavior, it was critical because having having tension on the cable can change the way in which animal escapes. So we study escape behavior. So then, yeah, it was really critical to do that for us. It might be that with the new type of cable, which is long and very, very soft, is less important to have a rotary joint. The other thing, I guess, is also matters is the duration of your recording. So my experiments are like usually 5 hours long. So in 5 hours, with the animal walking around a lot, so the cable can get really, really tangled. Maybe if you have shorter experiments, then that's not a problem.
A couple questions about the recovery, like what's the expected recovery rate of the probes? Like how frequently do you successfully recover them?
Yeah, so I was saying, I would say 80 to 90% our success rate, And the failure, the part that failed is when you extract the probe, because it can be that the shank remains in the brain. But yeah, I think it's, I would say 85%, something like that, can be the success rate with this technique.
Related to that, and also related to another question that asks about whether there could be a sort of a device that you design that allows removing the probe at the end. There's going to be a, maybe I'll just say briefly, there's a design from Sebastian Hessler's lab. I don't know if have you seen that, Dario, or have you used it?
No, so I think also in the next talk, no, they're going to be, Yo is going to talk about it.
Yeah, Yo's going to talk about something. Yeah.
So there are a few of them available. I mean, they make a slightly more complicated, I guess, the whole procedure. So since this approach worked for us, then we just stick with that. Yeah, it's not 100%, but I don't think also those methods are 100% success rate. So we were quite happy with the.
Yeah, so I guess the one from Sebastian Hessler's lab, there will be a description of that in upcoming Neuropixels 2.0 paper that's going to be on Bioarchive before too long. And that one has this kind of thing where there's like multiple parts and they fit together in a certain way, and you can separate them and pull the probe out in a controlled way. And I think, as Dario says, I agree that there's just the trade-off between how easy you want the recovery to be versus how easy you want the surgery to be, and how simple the implant is in the first place. And Dario's approach is definitely sort of the most direct or simple implant style. This is also very similar to what I had done in the past. Yeah. Some questions about how long can these implants last and how stable are the signals across days?
Yeah. So, well, for let's say the mechanical part, I've done some experiment with the dummies, and the implant was there 1.5 years after I implanted it. So the mechanical part is very, very stable. About the activity, so my experiment were usually, I don't know, maximum 2 months long. I never did longer than that. And usually in terms of units, so you have a very, very good signal in the last week. And then in my experience, they kind of plateau. And after this plateau, the signal is stable for a long time. Meaning that you will have few tens of neurons for, I think, these 2 months, and before you can have many more. That's the kind of, I don't know if you had the same experience, Nick.
Yeah, we definitely have some experience of declining numbers of neurons over days. I'm not sure, it sounds like for you, it's maybe like by a factor of 5 or 10, getting the number of neurons getting smaller?
No, it's a bit less. So, also, I mean, yeah, a factor of 5, yeah, probably.
Okay, yeah, I think in some cases we've seen maybe better persistence than that, more like by a factor of 2 or less.
Okay.
But yeah, I mean, I think in general, the observation that Dario makes is what we've seen too, that you sort of have some declining quality, but then it gets to a stable state, and you should have good yield for more or less indefinitely. There's a question about whether there's any lab currently working with chronic neuropixels implants in macaques.
I don't know.
The Livingston lab at Harvard, we heard, was doing that. I have not seen their data, but Margaret Livingston would be the person to ask, I think. Let's see, what is this?
There's a question about whether the signal is stable across sessions and days. And I guess also this will be addressed by Anna Lebedeva's talk, but.
Oh, you mean if you can record the same neuron across?
I guess that was the question, whether it's the same neurons. Do you have any idea?
No, so we didn't try to quantify that. So that's that I don't know. I mean, there are some obvious. So something I can say is that we try with SEPI, the post I mentioned at the beginning. We try to record from the same neuron in freely moving and at fixed. and that we could do successfully if the recording was spaced a few hours between one and the other, while when we try to do this maybe the day after, etc., the fraction of cells that we could track was lower. So
did you try to spike sort two sessions together? No.
Yeah, so this was more work that she was doing, but yes, so we try to do that, and we try then to match also the coding properties of the neurons in freely moving at the fix, etc. And we realized that it was better to, I mean, if the spacing between the session was few hours rather than.
Okay, so quickly.
But I guess, yeah, Anna did some better.
Diogo asks, how do you know it was the same neuron?
Well, exactly. So we are very, very careful with that. So what we did was we have a series of parameters. So we have the spec shape. We are studying various properties like at direction, at velocity, etc. So we try to match those one and to see if neurons which have similar spec shape as the also the same coding properties. But it could well be that was another neuron which had the same spec shape and very similar coding properties. I mean, it is not very easy to do this kind of statement, but yeah, I guess I don't know what else now in your lab you are trying to do this more systematically.
Yeah, we're using a trick about visual stimuli, which will be explained in an hour or so. There's only 1 minute left and 2 questions. Gretel's question came first. Nick, do you want to say that?
Yeah, I think if I understand Gretel's question, this is something like this is what Yo is going to talk about. So let's Gretel come back to that question if Yo does not answer it in his talk after the break.
And then we have Jaron's question about the general quality profile of the chronic recordings. Like, does it go bad for like 2 days after implantation, then it gets good, or you know?
No, it's usually very, very good the day in which you implant it, and then it starts slowly decreasing. But for the first week, I mean, can be 5 days or 8, but it's like good, and then it start decreasing more substantially. So if you really want to get a lot of neurons, I guess I would really suggest to do your experiment in the first week after the implant. If you're happy with the slightly less number of neurons, you can also keep going and record for
awesome.
a longer time.